So section 14.2 is really nothing different than section 14.1. There's just a lot of algebra. So the key things to remember are that when you're taking the partial of f with respect to x, you hold y fixed and differentiate with respect to x just as you would in Calc 1. When you're finding the partial with respect to y, you hold x fixed and you differentiate with respect to y just as you would in Calc 1. And of course, just as you would in Calc 1, remember that you have to carefully apply all those rules, the product rule, the quotient rule, the chain rule, etc., etc. So we're just going to carefully do a couple examples, some computational examples. So this first one is a partial derivative with respect to x, and it says take the derivative of this polynomial looking thing, and everywhere I see an x, I'm just going to pretend that that piece is just a constant. And then the derivative is pretty straightforward. So as I differentiate this first term with respect to y, I'll get 3x to the 5th times the derivative of y to the 7th, so that's times 7y to the 6th. In the next piece, 32x to the 4th all acts as a constant, so this is minus 32x to the 4th times the derivative of y cubed, so that's times 3y squared. Here the term 5x is a constant, and the derivative of a constant times y is just that constant. So we get plus 5x. And in this last piece, notice that there are no x's, that's fine. It's just plus 9y, so its derivative is plus 9. And we could clean this up just a little bit. 3 times 7 is 21, so that's 21 x to the 5th, y to the 6th. 32 times 3 is what? 96. So minus 96 x to the 4th, y squared, and then the rest is fine. Plus 5x plus 9. So this next one is decidedly more messy, and there are two steps. So first we're going to find the partial derivative of f with respect to x, and then we're going to evaluate it at the point pi over 3 and 1. And notice that the function of x and y has a couple x's. There's an x out there and an x out there. So that's going to make things just a little bit messier. So let's just be careful. So when I take the derivative with respect to x, first there's going to be a product rule. So there's x times the partial with respect to x of the rest, log of y cosine of x, plus the other way around, so log of y cosine x times the derivative with respect to x of x. Okay, so the first piece, now the x is inside the parentheses, so there's going to be a chain rule. So let's go through that carefully too. So there's x times the derivative of log of something. So the derivative of log of something is 1 over all that stuff, y cosine x, times the derivative of the inside, so I'll carry this one more step, the derivative of the inside, the derivative of y cosine x. Let's just leave that for a minute. On the other side, there's simply this derivative with respect to x of x, so that's just 1. So that one cleans up nicely. That's simply log of y cosine x. Okay. Now for this last piece, we need to differentiate this. Y acts as a constant, and so I'm taking the derivative with respect to x of a constant times cosine of x. So finally, that's not too bad. This first part that I'm just going to recopy is x over y cosine x times the derivative of y cosine x, so that's times y times the derivative of cosine x, which is minus sine x, and then let's just copy this other bit, log y cosine of x. Okay, so the next step is going to be to evaluate this derivative at pi over 3 and 1. So that is, we're going to want to take this partial derivative that we just found and evaluate it at pi over 3 for x, and 1 for y. And notice that y equals 1 is kind of nice, and so each of these multiplicative factors of y will have no effect, but I'm going to need to find the sine of pi over 3 and the cosine of pi over 3, so I'm just going to do a little bit of quick work over here. So this is the way I remember it. If that's pi over 3, then this is a 1, 2, square root of 3 triangle, and so cosine of pi over 3 is a half, and sine of pi over 3 is the square root of 3 over 2. So I'm just going to plug all that stuff in wherever it goes. So here's what we get. So that x is pi over 3. So I get pi over 3 over 1 times cosine of pi over 3, so that's over a half, times y, which is 1, times minus sine of x, so that's minus square root of 3 over 2, plus, let's see, log of y is 1, and cosine of x is a half. Hopefully I haven't made any mistakes. And so I think I have just enough room to squeeze in the final answer here. Let's see, pi over 3 over a half is pi over 6, so that's minus, in the denominator I'll get a 12, I think, and then a pi times the square root of 3 in the numerator, plus log of a half. And we're done. So let's do one more example from physics. This example is about the energy of a body of mass m moving with a speed of v, and presumably this is a relativistic thing because this energy has this factor that has to do with the speed of light. So the energy of this body is given by mc squared times this factor, which takes into account the percentage of the speed of light that the object's traveling. And ultimately our question is, what's the rate of change of the energy as the mass changes, that is the partial of E with respect to m, and what is the rate of change of the energy as the velocity changes, the partial of E with respect to v. So that's the idea, and we're going to interpret it a little bit and think about the sign of these two partial derivatives. And so I'll copy this onto the next page so that we have more space. Okay, so the easy one is taking the partial derivative with respect to m, because there's only one m in here, and the whole rest of this expression simply acts as a constant. And so it's very straightforward to write down this first partial derivative. The partial derivative of e with respect to m, differentiating with respect to m, is simply c squared times all of this mess in here, 1 over the square root of 1 minus v squared over c squared, all that minus 1. So let's think about what the sign should be in two different ways. Let's just first think about what we expect it to be, and then algebraically see if that's the right thing. So as the mass of the object increases, you would think that its energy would increase as well, I think. So let's see why the algebra bears that out. Remember that the velocity, I think I wrote this on the first slide, but maybe I didn't say it. We're going to assume that the velocity is always less than the speed of light, and in fact not negative. So if that's true, then 1 minus v squared over c squared, so this v squared over c squared term is a number between 0 and 1. So 1 minus that number is still a number between 0 and 1. And when we take the square root of that number, it's still going to be between, sorry, that should be a 0 over there, 0 and 1, and not equal to 0. And so if I take that number and I plug it back in here, 1 over that number will be bigger than 1. If I subtract 1, it's going to be positive. Okay, so this expression here, all of this will be positive. Okay, so the partial derivative with respect to m will be positive. Next, when we want to take the partial with respect to v, that's going to be quite a bit messier because this v is buried way inside here. So the first thing I'm going to do, I think, is rewrite this a slightly different way, which might make life a little bit easier. So let's write this as mc squared times 1 minus v squared over c squared to the minus 1/2, minus 1. That's just going to help me not make too many mistakes. But let's point out a few things. I'm differentiating with respect to v, and so the v is in here. This piece, mc squared, this time that acts as a constant. Okay, so the partial of v with respect to v, well, there's the constant piece out front, so let's just copy that down, mc squared, times the derivative of all that stuff. Okay, so let's take the derivative of the first piece. There's going to be a chain rule since the v is buried inside. So I'm differentiating with respect to v. I get minus 1/2 times the stuff inside, 1 minus v squared over c squared. Decrease the exponent by 1, so we get minus 3/2, times the derivative of the inside. Okay, so the derivative of 1 is 0, and then I simply take the derivative of this with respect to v. So, times minus 2v over c squared. And finally, the derivative of 1 is 0, so that piece just goes away. Okay, so let's clean it up just a little bit, but not too much is necessary. So notice that there's a minus 1/2 times minus 2, so that's 1. And then there's a c squared divided by c squared, so that's 1, and that also goes away. And so let's see what's left. So there's still an m, and let's see, the minus 1/2 times minus 2 was 1, the c squareds cancel. There was a v left over, so there's v, and then there's this term 1 minus v squared over c squared to the minus 3/2. And if it helps you, we could write it this way: m times v over the square root of that mess on the inside, 1 minus v squared over c squared cubed. So finally, let's think about the sign. So again, as the velocity increases, I think you would expect the energy of the body to increase. And algebraically, in fact, this one is even easier than the last one. Remember, v squared over c squared is a number less than 1. So this term is 1 minus a number less than 1, so it's positive. So in fact, everything in sight is positive. So this partial derivative is also positive.